We met Lorenzo more than 20 years ago, and I don't remember if this is the first time, but there was a memorable workshop on dynamical system in southern of Chile in Las Cascadas, near the Osorno volcán and Yanquihue Lake. In that conference, an intense soccer match was played between professors and students, and the professors got a glorious, really glorious draw, thanks to the goalkeeper who stopped impossible shot, really impossible shot. In that match, Lorenzo played with nothing to envy to Iribar or Zubizarreta. So thank you, Lorenzo, for your friendship along these years and your generosity, sharing a wine, a talk, a wisdom, or recite. So I hope we can share a wine soon. Okay, happy birthday. The setting that I will speak today is I like to consider a time one map of a geodesic flow, defined on a orientable compact Riemannian manifold with constant negative curvature, and I will consider the Liouville measure on M. The main theorem, which is actually an application of a very general result. I will mention that this work is collaboration with Radu Saguin and Francisco Valenzuela Enriquez. The main theorem is, in this case, when we consider C2 families of diffeomorphism passing through this time one map, the map of the topological entropy is differentiable in the time t equals 0. I mean, in the time one map of the geodesic flow. This result well, let me to say something about that. The first novelty is we don't consider just surface. The result is no for surface. When the original manifold is a surface, we have not a hypothesis about the dimension of the stable or unstable direction, and moreover, we can compute at the end of the talk explicit formula for the derivative. Some remarks necessary. The Liouville measure is a measure which is invariant under F, and is the unique U-given state. That meaning the measure is absolutely continuous, have a conditional measure along the unstable variation, which are absolutely continuous with respect to the Lebesgue measure along the leaves, and is the unique one. This is a special, and this situation happened in the time one map of the geodesic flow, but it's not a general situation even in an ozone. No? Well, probably an ozone, but in general, that is not true. And the Liouville measure is also the unique measure of maximal entropy. Okay. Okay. Another remarks. There is the diffeomorphism is partially parabolic. The center dimension, the center direction has one dimension, but as mentioned before, we don't know. We have not any hypothesis about the dimension of the stable or unstable bundle. And in this case, the splitting varies C1 with the point, and we can say also that there exists a neighborhood of F. Well, all the diffeomorphisms belong to U, C2 neighborhood, sorry, are partially parabolic, and entropy expansive with constant of entropy expansiveness uniform, which implies that every diffeomorphism in the neighborhood has an ergodic measure of maximal entropy. Also, every G in U has an ergodic Gibbs U state. So our first result is for our family is the measure of maximal entropy converged to the Liouville measure, and the measure the U Gibbs state converges to the Liouville measure as t goes to 0. The second item is well known. The first item, the convergence of measures of maximal entropy, depends strongly of the fact of this uniform epsilon entropy expansiveness. Well, how we prove the theorem A? Basically, we have two bounds for the topological entropy. One is come from the real formula, which we know that the topological entropy is bigger than all the sum of the maximum, in this case, of the LYAPUNOV exponent along the sum of the LYAPUNOV exponent along the unstable direction, or about the positive, or the sum including the central LYAPUNOV exponent if the central LYAPUNOV exponent is positive. So we have here the maximum, and we can define this function. We call the function AT, A dependent on T. We have another inequality a bit due to the Lapierre-Young formula. We say the topological entropy by variational principle is bigger than the entropy of the U Gibbs state, which is bigger than the unstable LYAPUNOV exponent. Here, for me, LYAPUNOV exponent means the average. I will give a precise definition in a little bit more, but here lambda u is well, if the dimension is bigger than 1, means the sum or the integral of the logarithm of the derivative. You know? So we have to prove that a and b are differentiable in 0. That means, and the derivative we want to say that is equal in 0, and we need to prove that the derivative along the center direction of the LYAPUNOV exponent with respect to the measure of maximal entropy is 0. Yeah, is 0. So linear response, which mean is related with the derivative of the entropy, is related with the derivative of the LYAPUNOV exponent. From the claim 2, since the derivative of the central LYAPUNOV exponent, we can reduce to the derivative to the unstable LYAPUNOV exponent or we respect the measure of maximal entropy. So it's just necessary to prove the theorem to show that the unstable LYAPUNOV exponent are differentiable and the central are differentiable all in t equal to 0, and to prove that the derivative with respect to the measure of maximal entropy or with respect to the u-give state are the same, and the central the derivative of the central LYAPUNOV exponent is 0. So let me say what we proceed. In general, we put this situation, this problem, in a little pane setting. The LYAPUNOV exponent, well, we assume by now that we have a splitting preserving by the derivative, but this splitting is not necessarily, invariant splitting is not necessarily dominated. Yeah? We have in mind E, for instance, to be the central direction and F to be the stable plus unstable direction. So in this decomposition is not dominated. You know? We assume so in this, for this decomposition, we define the average LYAPUNOV exponent of ft respect to a like as the integral of the logarithm of the determinant of the derivative along the respective direction. That is the classical definition, but we want to give another, put this notion in another context, which was we first see this this notion in the book of Marcelo, and we use the geometry, well, the formalists coming from the differential form, and we do the following. For the A direction, we choose a base. Of course, this base for the A direction depends on the point and conform a K multivector field, where K is the dimension of the space A. And we can choose for the 10-1 map, for instance, another element in a K-form, differential form, such that when we apply the differential form to the multivector field, this is normalized, and the kernel of the differential form coincides in some with the other direction. And we choose the initial multivector field and the differential form. We can choose for the form of is close to F, the multivector field for the respective space of subbundle A, and provide and choose constant in such that the K form, the K form omega in the space is equal to 1. The differentiability of the space of the subbundle A and F gives some allows to have a differentiability of the form, the same of F in this case, and the differentiability of the multivector field. So we denote by star the action induced by the derivative, and so there exists a number we call eta, which represent in the determinant. So when we apply the derivative to this multivector field, we obtain a number which is the determinant times the multivector field in the image. So applying the omega forms to this equation 1, and recalling that the omega form is normalized the multivector field. So we have an integrating respect to the measure mu t, we obtain that the integral of the log of eta t the mu t is equal to the logarithm of this form applied to the image of the multivector field by the derivative. So here is we can see that if we want to obtain differentiability of lambda, we precise to have some differentiability of course of f of the family of the of the subbundle V A, which the subbundle A define the multivector B, and the subbundle, the complementary subbundle, which define the K form. So finally, when we consider a curve of with a family or one parameter family of the diffeomorphism, we can consider the difference or the variation in some sense of the initial diffeomorphism with respect to the family, and when we derivate that is H, and we derivate this function of this family, we obtain a vector field which is tangent to H, and we can say, so we can see the perturbation in some sense. We can write the perturbation like a flow, which is generated by this vector field, plus higher order terms. This is important because we want to obtain explicit formula to compute the derivative, for instance, to the central derivative, and to know if the derivative is zero or not, and compare the derivative obtained for measures of maximal entropy and for PUCV state. So the remaining is just to put this the element in like in a Taylor expansion, and B T, for instance, is V, is the plus T times the derivative, because B is considered C1 plus other terms. We can prove that the derivative in this case is in the kernel of the form, and the action of the derivative of H on a multivector V here appear is given by, well, H is morally the identity plus other terms, and the derivative is the action of the vector field generated by the derivative of H, this is X, applying on the multivector field V. So if we try to compute eta t, putting the formulas above together, we can compute eta t like in this way, like a variation of eta, and so we obtain that the logarithm of eta t is the logarithm of eta minus t times the action of the K form on the least derivative along the vector field generated by the perturbation on the direction, the multi-vector field, which is the base of the E sub-bundle. And so we can, integrating, we can obtain the, reobtain the LYAPUNOV exponent, like the integral, like this integral here. And so, well, of course, to see the differentiability, well, this part, let me try, I don't know if, so I can, well, this part is, of course, should be part of the derivative, because this expression. But in order to know if the exponent, the lambda, either is differentiable or not in t equal to 0, depends on if this integral is differentiable with respect to the measure, which is varying. So this is that we know by linear response, or we call linear response. And if this integral is differentiable, so we have the LYAPUNOV exponent is differentiable, and the derivative is the linear response, which is the derivative of the first integral minus the second integral. So we say that mu t has linear response, that is a real number with respect to a function phi if the map where fixed phi and move the measure is differentiable in t equal to 0, and r phi represent the derivative. In particular, if the function phi is constant, we have any family of measures have linear response, and in this case, the linear response is 0. So we have a second theorem which summarizes this consideration. When you have in our setting, we have a splitting, not necessarily dominated, but C1. So the LYAPUNOV exponent, the average LYAPUNOV exponent, with respect to this, the subbundle E, is differentiable in 0 if and only if the family of measure has linear response with respect to the logarithm of the determinant.
Oh, sorry, Carlos.
Yeah?
Here you are assuming the hypothesis of the previous theorem, or for instance, do you need entropy expansiveness or something like that?
No. He is a very general result. We are assuming we have a diffeomorphism F having a splitting in two subbundles invariant by the derivative, and the splitting is not necessarily dominated, but one of the subbundles is C1, the other is maybe, well, it's enough to have a C1 for this result. And we consider a family mu t of measures converging to the limit measure mu. Just that. And to obtain the differentiability, the theorem says that it's enough to have linear response for the first part, and we can obtain a formula, this formula, like a formula for the derivative. Okay.
All right. What is lambda?
Lambda is is the, let me. Okay. Lambda is the, well, let me.
Lambda is okay.
We have.
But okay, no, this is what my question is. So you have invariant splittings. So
yes.
you're not assuming domination. Are you assuming continuity of these splittings? Do you assume that they depend continuously on T?
We well, we are assuming some regularity in the split of the point, but we can obtain a la Dolgopiat some that this is enough to obtain some regularity of the splitting with respect to T.
Okay, so you want some kind of, you basically want the sum of bundles that come from a dominated splitting.
Sorry?
You want a sum of two bundles, and the bundles themselves are sums of bundles in a dominated decomposition. I mean, in practice, because you want them to depend continuously on T.
Yeah,
Okay, I mean,
yes,
it's like what you said, you want E to be like the center and F to be the stable plus the unstable.
in the practice, like in the example that or the application, the subbundle has not the subbundle E is not dominated by F.
No, I know, but the bundle E is a bundle in a dominated decomposition. And F is the sum of two bundles that are in a dominated splitting.
Yeah,
and so those sub bundles depend continuously. So that's kind of the setting. That's all.
Yeah.
It's like Dogopiat's paper on differentiability of SRB states.
Yeah. That in fact, our main inspiration are your work which Mike showed and the work of Dogopiat. We mix a little bit about of the idea. I try to back to the theorem. Well, that is our theorem. So we obtain differentiability with this form for the derivative. It's interesting that here is in this formulation is clear that the derivative depends on the or the regularity depends of both regularity of E and depend in some sense of the regularity of F. Okay, the both. So well, the rest. In the case of the geodesic, the time one map for geodesic flow, the unstable sum is constant for F because the curvature is constant. So as observed before, the linear response is 0. So since the linear response is 0, the derivative just depend, it's just this integral, which doesn't depend on the measure mu t, the mu t, the family of measure considered. So we obtain that in the case of the unstable Lyapunov exponent, the derivative, both are differentiable and the derivative coincides, like we want to prove initially. And we can compute with the splitter formula the central Lyapunov exponent. In this case, we have a form defined by the sum of the stable and unstable subbundle and applying to the Lie derivative along the vector field that we can show in this case, like saying the vector field generated by the geodesic flow, and we can, after a computation, we can conclude that the derivative is 0, like we want. So actually, we can prove a little bit more. We have the family of time one map. We can conclude the entropy, the topological entropy is differentiable and t equal to 0, and we know how much the derivative is the integral of the form along the central stable direction applied for this Lie derivative on the vector field associated, multi-vector field associated to the unstable direction. Okay. Well, I think for me it's enough. So thank you very much for your attention.
Okay. Do you have any questions, comments?
Carlos, you tried to in the last slide, in the previous slide, you tried to prove this result for, say, partial hyperbolic diffuse with one-dimensional center. Where is the first step where the proof failed? I don't know, that this is not very polite.
No, well, I keep failed. Several things failed. One of them is if you are in that general setting, yeah, well, a partially hyperbolic setting.
One-dimensional centers, you have 3D direction.
I think you in principle there's two things which are not clear. One is the uniqueness of the U-Gibbs state. But
Okay.
yeah, this is a problem because when you perturb, okay, the perturbation we consider here doesn't preserve the neither Liouville, neither Lévesque, neither are not conservative. We can do that in a very general way. It's well known that the U-Gibbs state converges to U-Gibbs state, but in general, the map, the limit map, in general, have more than one U-Gibbs state, so you have not control where are you converging. Now, this is an initial problem. Another problem is the existence of measure of maximal entropy in general. You need to guarantee that. And well, and of course, if you consider kind of algebraic diffeomorphism in order to obtain differentiability of the splitting pointwise or respective point, I think maybe the rest should work, but I don't know in general.
Thank you, Carlos.
Okay, any other questions? Well, if not, then let's thank all the speakers of today.
Thank you.
I have a word to say. Yeah. No, okay, let's thank Carlos. Sorry, Misha, that was not planning, but anyhow, the point is that you know that Lorenzo is one of my dearest friends, and then I collected some memories, and people who knows him quite well will recognize the expression that he used to use either when he is happy or he is criticizing or he is ironic or he agree or disagree with you. And then please, just a moment.
This is recorded.
No, please, then you can